Coming up next, we have Kyle Schomp talking about DNS record injection. As Kyle makes his way up here, I have a survey giveaway to give away. Is Steve Surdock in the room? Steve Surdock, you have won an Xbox One, courtesy of Microsoft. You can pick it up at the registration desk. Great, thanks a lot, Steve. And everyone, please do fill out your surveys. We have a winner. You could get the next Xbox One. Thank you.
Is there a way for me to see the slides?
Yeah, your slides will be on there. Great. Here's forward, here's back.
Oh, okay.
Timer's going.
Okay. Hi. My name is Kyle Schomp. I'm here from Case Western Reserve University in Cleveland, Ohio. And recently we've been studying the security of the domain name system, and I'd like to show you some of our findings. In particular, this talk is about record injection attacks. And when I think about record injection attacks, I typically think of the target as a shared recursive resolver like those run by an ISP, or more recently, public resolvers like Google or OpenDNS. Things like bailiwick violations or the Kaminsky vulnerability can be used in an attempt to insert insert fraudulent records into the resolver's cache. And these shared resolvers are, of course, a tempting target precisely because they are shared. So one successful attack has many thousands of victims. But now we have mitigations against these known attacks. For example, the bailiwick rules can protect against authoritative DNS servers returning arbitrary records and responses. And also transaction ID randomization, ephemeral port randomization, and 0x20 encoding protect against off-path attackers. In a study from 2 years ago, we actually found that the bailiwick rules are nearly universally applied now, which is a very good thing to see. And most servers are patched to perform ephemeral port randomization. We still found 16% of resolvers are unpatched, but we also found a positive correlation between the likelihood that a server is patched and the number of users the server supports. So that 16% of resolvers actually count for far fewer people. So all in all, this kind of paints a picture that security against known attacks, at least, is looking okay at the shared resolver. Therefore, my security group decided to look at a different problem, open resolvers. Now, we've all known that these things are an issue forever now, it seems like. But the Open Resolver project is still showing there's 27 million of them on the internet today. And this is actually almost double what researchers found back in 2008. Recently, the Open Resolver project has shown a decline, and we can hope that trend continues. But in the meantime, we'd like to answer this question, just what are open resolvers? So, we came to the conclusion that open resolvers are home routers. And in discussions from yesterday, it seems that other people have come to the same conclusion. Always nice to see independent people come with the same answer. We have some evidence to support this hypothesis. When you look at a random sample of open resolvers on the internet, we see the following attributes. A quarter-run ROM pager, which is a popular embedded web server application. A quarter provide a basic HTTP auth realm and HTTP responses, like the example I show on the slide there. Almost 70% are on policy block lists, which, among other things, tend to have residential locations. Also, we see that nearly half of them actually return DNS responses on the wrong port, so any port other than 53. We attribute this behavior to an erroneous self-natting, where the device is actually performing network address translation on its own packets. Finally, we also look to see if popular names are in the Open Resolvers cache, and we find that many actually include names from the Alexa Top 1000, and that would indicate to us that they're probably in use by people. So together, if we sum it all up, we have this idea that open resolvers are, at least in the majority, used low-end embedded devices in residential locations, or most likely home routers. So if these things really are home routers, then we actually already know something about their DNS behavior, right? They're simple forwarders. They accept a request from a device within the home network, forward the request to an upstream resolver, like an ISP's or Google Public DNS, whichever, cache the response, this is an important point, they cache the response that they get back from the upstream resolver and then return that response to the device within the home network. Very simple. What could go wrong? Besides, of course, that home routers are already acting as open resolvers, which is not good. So, as I mentioned on the first slide, in the past, serious vulnerabilities have been found in shared resolvers, right? And if a shared resolver can have a vulnerability, why not that tiny little box sitting in your home that you probably haven't touched in years? Well, not surprisingly, we found one. It turns out that a lot of these boxes simply do not validate DNS responses. They don't check anything. We call this the preplay vulnerability because an attacker can generate his packets beforehand with no guessing involved at all. When we looked for this, we found that 7 to 9% of open resolvers have this vulnerability, and that equates to about 2 to 3 million boxes on the internet. Also, when we scrape port 80 on these things and parse through what we get back, we were able to identify a few different models from a few different vendors. So this doesn't seem to actually be a vulnerability in one specific device. It's much more widespread than that. Here's an example of how the preplay attack might be used. So in this case, the attacker sends a request for a name to be poisoned to the home router and immediately follows up his request with a response. Since the attacker sends these two back to back, the response will arrive before anything from an upstream resolver possibly could with very high probability. The home router will cache this response because it doesn't perform validation. And sometime later, a device within the home network will send a request for the same domain name and receive the poison. So that's preplay. But it turns out, actually, when we looked a little past this, there's actually some more here. Preplay doesn't require any guessing on the part of the attacker. But there's actually a significant set of home routers that are protected by exactly one unknown variable, the ephemeral port number. If an attacker can guess that, then these boxes should be easy to poison as well. But there's 65,000 possible port numbers, right? So if you're just attacking a home router, maybe it's just not worth your time to try and guess them all. It turns out, though, from our results that these boxes don't select the port number randomly. The graph here shows port numbers we found vulnerable in a random sample. And two things to note here. First, almost 50% of the ports are within the range 1,000 to 5,000. It's a rather small range. We believe that these boxes are simply selecting the first available external port number in the NAT to use for DNS. Second, there's a large mode at 32,768, which is a number probably everyone here is familiar with. So this is clearly not random. And for these boxes in these two areas, in the mode and at the 1,000 to 5,000, the attacker doesn't have to actually explore the entire range to poison this box. So you might see, okay, these are attacks against home routers, but why would a bad guy ever want to attack a home router in the first place? There's clear trade-offs between attacking a home router and a shared resolver that I'd like to cover here. Number one, the attacks, like Kaminsky vulnerability, are complex in nature against shared resolvers, whereas what I just showed you, attacking a home router, is actually quite trivial. So pretty much anybody could do it. Second, of course, when you're attacking a home router, the only potential victims are the household. But when you're attacking a major shared resolver, you could have potentially thousands of victims. That comes with a downside, though, in that most of the time, if you're attacking one of these popular shared resolvers, there's a good chance of detection, because they're not dumb, right? But when you're attacking a home router, just no one's watching there, no one's looking. Finally, thanks to Kaminsky vulnerability, it's possible to poison whole domains when attacking shared resolvers. But because home routers don't handle delegation records, an attacker can only poison a single domain name at a time. As an aside, I'd also like to mention that record injection isn't the only reason why these things could be dangerous. As we've heard many times over, they of course aid reflection or DNS amplification attacks because they're open. But also they expose the closed portion of the resolver infrastructure. if an ISP closes their resolver for security reasons, but the home routers of the ISP's customers remain open, then it'll still be possible for an attacker to discover the ISP's resolver and subsequently attempt to attack it. All right, so that was all the bad news I have. But the real question then becomes just what can we do about this? And personally, I see there's kind of two options, and this is predicated on the fact that these things don't get updated. Like, some people might actually bother to go to their home router and update the firmware, but I know before I started doing this work, I didn't. So option one, what I view as sort of the bad option, would be to simply wait until this old hardware becomes obsolete and people have to replace it. Vendors are already, as I understand, working on adding automatic update features to the boxes they're pushing out. So in the future, either push or pull updates down to these boxes and patch vulnerabilities like this. Or option two would be to start blocking UDP53 to residential locations. We checked in our data set and found that nearly all of the open resolvers we found only accept DNS requests on port 53, as you would expect. So blocking would be effective. Some of these boxes also seem to use port 53 as the ephemeral port. So some care has to be done in how the blocking is performed. It probably needs to be at the edges of networks rather than right in front of the houses. But it's still quite feasible. Now, there is always the possibility of a third option here, and maybe some of you network operations experts out there can educate me on it. But I hope that through this talk I've at least actually convinced some of you, if you weren't already convinced, that something should be done about these boxes. And that's all I have for you. Thanks.